Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's video we're going to be looking at sequence summation and then moving towards understanding this difference transform. Okay, so we are working with basically two operations on sequences, the difference operation and the summation operation. So somewhat informally, if we have a sequence represented by a clip or just a bunch of numbers in a row, 3 dots, say A0, A1, A2, and so on, then the difference operator is the sequence of successive differences, A1 minus A0, A2 minus A1, and so on. While the summation is the sequence of successive partial sums, starting always with 0, and then A0, and then A0 plus A1, and then A0 plus A1 plus A2, and so on. And our convention is to always start sequences with index 0. So this is the 0th element, this is the 0th element, this is the 0th element, unless otherwise stated. Okay, this is somewhat informal because it's at the level of clips. We want to also understand what it is explicitly at the level of the sequences themselves. And then there's two cases, the cases of finite sequences or K sequences and the case of on sequences. So we're going to concentrate mostly on the finite sequences, the K sequences. So if S equals A0, A1 up to A, K minus 1 is a K sequence. So we have a specific sequence of numbers right in front of us and we can count them. They're right all there from the 0th one up to the K minus first one. Then the difference of S is A1 minus A0, A2 minus A1 up to AK minus 1 minus AK minus 2. Notice that there's now one less term than there was previously. We're going sort of from an index 1 here to an index K minus 1. So there's altogether a K minus 1 in this sequence. Taking the difference lowers the length of the sequence. On the other hand, taking the summation increases it. So the summation of this sequence S is always starting with 0, and then A0, then A0 plus A1, and so on, all the way up to the final sum, A0 plus A1 plus all the way up to AK minus 1. And if you look at it here, this is a K plus 1 sequence. It has one more term than does the original sequence. So for example, if we start with the sequence S equals 5, 7, minus 1, then the difference of S is 2 minus 8. Successive differences there. While the summation of S is 0, always starting with 0, and then 5, and then 12, and then 11. So oftentimes it's useful to have algebraic expressions which describe or determine sequences. So we'll use the following notation for that. We're interested in a K sequence and we'll allow ourselves to write it like this if we have an algebraic expression R of n. So it could be a polynomial, but it could also be something a little bit more general than a polynomial. So we have Rn, we'll put it in brackets with a square bracket on the left and a pointed bracket on the right, and then we'll have indices here, 0, K minus 1, telling us that this is going to be a sequence that starts with 0 and goes up to K minus 1. So what this means, this is the sequence R0, R1, R2, up to Rk minus 1. So it's a K sequence, it has K terms. And this will be valid for K equals 1, 2, 3, and so on. So for example, here is a sequence S. 1, 2, 5, 10, 17, 26, 37, 50. It's an 8 sequence. So it turns out that this sequence could also be written in this fashion. We can write it as S equals sequence 1 plus n squared from 0 to 7. Now, we could check that by just substituting the values here, and indeed these are the numbers which are 1 more than the squares, starting from 0 squared up to 7 squared. Okay, so let's look at this sequence from this algebraic point of view. The difference sequence, successive differences, 1, 3, 5, 7, 9, 11, and 13, can then also be expressed in terms of algebraic notation as the sequence of 1 plus 2n from 0 to 6. When n is 0, we have 1. When n is 6, we have 13. And we could obtain this just by taking the algebraic expression here and evaluating the difference, this expression evaluated at n plus 1 minus the same expression evaluated at n. So if we take that difference, it's basically n plus 1 squared minus n squared, which is 2n plus 1, which is what we have here. So we can take the difference at the level of the algebraic expressions. What about the summation? So the summation of this is 0 and then 1, 3, 5, add is 8, and then 18, and then 35, and then 61, and then 98, and then 148. So this summation sequence can also be obtained in an algebraic fashion, but it's more work. It's more work. But it turns out to be this thing here. So this is the sequence, nth term 7/6 n minus 1/2 n squared plus 1/3 n cubed. And it's a sequence that runs from 0 to 8. So how could we have gotten this? It's a little bit more complicated. So we would have to take this thing here and we basically have to sum this. So the nth term in general would be sum from j equals 0 to n minus 1 of 1 plus j squared. That's a typical partial sum of the original sequence. So how can we deal with that? Well, the summation here has two different parts. There's the sum of just 1 from 0 to n minus 1, which is n. And then we're summing j squared from j equals 0 to n minus 1. Well, that's just a sum of powers situation, sum of squares, and we know what the formula for that is. It's a Faulhaber polynomial of a especially simple kind known to Archimedes. And in this case, we take the n minus 1 and we put it here in n minus 1 times n times 2n minus 1, all over 6. So in this case, we can use our understanding of sums of powers to evaluate the summation of a sequence like this, which is given to us as a polynomial. So this is really the heart of the discrete calculus. It's sort of the fundamental problem, is to compute summations of sequences. Just as in the regular calculus, the heart of the matter often is calculating integrals. Okay, so the rough orientation is that calculating differences of sequences is generally easy, while calculating summations of sequences is generally hard. Okay, that's a generalization, but it's a rough orientation. And a key theorem that allows us to exploit the easiness or relative easiness of finding differences is what we might call the fundamental theorem of the discrete calculus, which relates the two operations of taking differences and taking summations. So we can write it in two parts. The first is this one here, that if you have a sequence S and you take its summation and then you take the difference of the summation, you get back the original sequence. And we've seen this already in a number of special cases. And the other way around, if we take a sequence S and we take the difference first and then we take the summation, we almost get the sequence back. But if the sequence does not start with a 0, there's no way we could get that sequence back because summations always start with 0. So the theorem is that the summation of the difference of S is S minus a certain constant, S of 0, the first term, or the 0th term of the sequence, times the constant sequence of 1. So it's basically the original sequence S, but reduced, adjusted by a constant sequence, so that the first term is 0. Okay, so there's an important corollary of this, an application, so that if we know that the difference of a sequence R is S, okay, then it follows that R is more or less the summation of S. In fact, it's exactly the summation of S plus some constant times the constant sequence. In other words, if we're trying to find the summation of s, we have some sequence s, and we're trying to find its summation. If we can find a sequence r whose difference is s, then that r is pretty well the answer. Okay? R is pretty well the summation of s, but you have to adjust it possibly by a constant to ensure that the first term of this r actually is 0. This is an immediate consequence of this fundamental theorem. So the idea is that if we know a lot about differences, if we have tables of differences of lots of sequences, then we're in a reasonably good position in terms of finding summations of sequences, because we can look for sequences whose differences are the ones that we have. So let us look at an example. Suppose we're interested in finding the summation of the following sequence. Sequence 2 times n plus 1 from 0 to 100. So we're trying to find the summation of s, where s is the following sequence. This is an algebraic form for the sequence that would look like if we wrote it out. Well, when n is 0, we start with 2, and then we go up by 2 each time. So it's 2, 4, 6, 8, all the even ones, all the way up to the last one, which will be 101 times 2, or 202. So that's the sequence, and I could, if I had more time and I didn't want to strain your patience, I could write out all the terms of that sequence and we could see everything in front of us. Note that I'm using 3 dots here to represent all the terms that I'm a little bit too lazy to write down. So this is a shortcut. And I want to introduce a little bit of terminology here, maybe to make a distinction between 3 dots. Okay, we use 3 dots a lot, and I want to separate one usage from another usage. So this lower dots, these lower dots where the dots are sort of at the base of the line, in LaTeX L dots, is really a shortcut. We want to use it as a shortcut. It means that we all know what's happening in here. It's just that we're wanting to save time and space, so we'll put these 3 dots instead. But the meaning is quite clear, in this case because we have the formula sitting right above us. Okay. So now let's look at what we want. We want to find the summation of this sequence. Well, we can do that at least to begin with. The first one is always 0, and then the next one will be 2, and then we get 6, and then 12, and then 20. And then it carries on in some fashion. But at this point, it's not entirely clear what the next elements are. I mean, it's going to carry on until finally we get to adding up 202. But there's some ambiguity here, and so I'm using centered dots, dots which are sort of written in the middle of the line, not at the bottom. These centered dots, like this, generally means and there's more. Okay, it's telling us that, there's something else going on in that direction, but we maybe don't have an entire handle on it yet. So I just wanted to use this. I'm not going to be completely consistent about this. I'm going to try to be consistent, but I will probably slip into ordinary usage. But I think it's nice to start distinguishing between these 2 different kinds of meanings of 3 dots, because the 3 dots are kind of important in mathematics. Okay, so let's have a look. What could this summation sequence be? So we look at it, 0, 2, 6, 12, 20. Is there some pattern there? Well, if we stared at it for a little while, we might see, well, this is the product of 1 times 2, and this is 2 times 3, and this is 3 times 4, and this is 4 times 5. Maybe there's a pattern. So let's guess that this summation is actually a sequence R, which is given by the pattern that's appearing here, sequence n times n plus 1. So when n is 0, we would get 0. When n is 1, we would get 2. When n is 2, we would get 6, and so on. And presumably, we're going to go up to 101, because there's usually one more term in the summation of a sequence. Okay, that's our guess. It's our guess that we've obtained by looking at the first few terms here. And now we want to ask, well, is that actually going to work? So let's check that by taking the difference of this thing here. The difference of this we can compute because it's relatively easy. We look at the value at n plus 1, which is n plus 1 times n plus 2, and subtract the value at n, which is n times n plus 1. And we're going from a 0 to 100, one less than the sequence that we start with. What's inside here simplifies to 2 times n plus 1. And once we've done that, we see that indeed the difference of r is the original s that we found. So from the fundamental theorem, that allows us to conclude that this r has to be the summation of s up to some constant. So we can write r is equal to summation of s plus some constant times the constant sequence 1. And we can determine that constant sequence 1 by evaluating the left and right hand side at some particular value. Let's say at n equals 0. At n equals 0, r has the value 0, and sigma of s has to be 0 because all summations start with 0. So that allows us to conclude that this c is actually equal to 0, and indeed this r is entirely the summation of s. So we found the summation of s, it's the sequence n times n plus 1 from 0 to 101. Example of exploiting the fact that knowing about differences can tell us about summations because they're sort of inverse operations. There's another important technology for finding summations of sequences that involves the Harriot basis and the Gregory-Newton formula that we talked about last time. So I remind you that the Harriot basis is a special family of sequences. The sequence 1, sequence n, n choose 2, n choose 3, and so on. These are the columns of what we call the Harriot matrix, and we're calling them H0, H1, H2, H3. So these are sequences, they're actually on sequences. And the pleasant property about them is that they behave very nicely with respect to differences and summations. The difference of hk plus 1 is hk. So the difference of h3 is h2. The difference of h2 is h1. The difference of h0, however, is 0. And in terms of summations, it's exactly the opposite way. The summation of h1 is h2, the summation of h2 is h3, and so on. hk gets sent to hk plus 1 under summation. For any k equals 0, 1, 2, and so on. So the idea is that if we have a sequence and we can express it as a linear combination of the Harriot sequences, then performing either differences or summations is relatively trivial because we know how these operations act on the Harriot basis elements. So the Gregory-Newton formula tells us how to express a typical Pauli number on sequence in terms of a linear combination of these Harriot sequences. And the formula is that if p is a Pauli number of degree k, or if you like a polynomial, then the associated on sequence, this is our terminology for on sequence, p0 plus, can be expressed as a linear combination of h0, h1, h2 up to hk. And the coefficients are just the various differences of p evaluated at 0. So p of 0 times h0, difference of p at 0, the squared difference or the second difference of p evaluated at 0 there, times h2, all the way up to the kth difference of p evaluated at 0 times hk. So combining these two, this gives us a powerful tool for calculating summations, also of finite sequences. So let me illustrate this. Here's an example of a sequence, s equals 3, 4, 7, 8, 10. So it's a sequence with 5 elements. It's a finite sequence. And suppose we're interested in finding the second summation of s. In other words, the summation of s. So we'll allow ourselves to perform multiple summations just as we perform multiple differences. Okay, so the key is to get a handle on this sequence by finding its differences. We make a difference table starting with the given sequence. There's 3, 4, 7, 8, 10. We compute differences. 4 minus 3 is 1, 7 minus 4 is 3, 7 minus 8 is 1, 10 minus 8 is 2. And then differences here, there's a 2, there's a minus 2, there's a 1, and then here, difference minus 4, difference of 3, and over here, difference of 7. So these are the successive differences of S as far as we can go. We can't take any further differences. And the top elements of each one of these gives us a new sequence in green, sequence 3, 1, 2, minus 4, 7. And we're going to give this a name. We're going to call it T of S. Here it is again, 3, 1, 2, minus 4, 7. We're going to call it the difference transform of S. So we start with a sequence S, which is this one here, has 5 elements. It's a 5 sequence. And here, the difference transform is 3, 1, 2, minus 4, 7. It's what we get when we make a difference table and then look at the 0th elements, successive elements of the successive differences. The reason why this is important is because the Gregory-Newton formula then allows us immediately to write down the original sequence in terms of a linear combination of the Harriot sequences with exactly these coefficients. So S is then the sequence 3h0 plus h1 plus 2h2 minus 4h3 plus 7h4, and it's a finite sequence, so it goes from 0 to 4. So we'll write it like this. So the advantage in this representation is that now taking summations is easy, because the summation of h0 is h1, the summation of h1 is h2, and so on. And summation is a linear operation on the world of sequences. So the summation of this linear combination of h's is going to be this linear combination of h's. We'll just jack up each one of the indices by 1. And now it's going to be a sequence that goes from 0 to 5, because taking the summation always extends the sequence by 1. And if we want to perform another summation, well, then we just increase these by 1 yet once more, and then we end up with a sequence from 0 to 6. So if we want to write down what it is in terms of value n, well, we would use the fact that the kth Harriot sequence evaluated at n is n choose k. So we can replace h2 here with n choose 2, n choose 3, n choose 4, n choose 5, n choose 6, and then we could obtain an actual polynomial that passes through the values here. It's a polynomial of n. What is actually the sequence itself? Well, I've made a computation over here. Let's see what it is. In terms of actually a sequence, it turns out to be 0, 0, 3, and then 10, 24, 46, and 78. So that actually explicitly is the second summation of the original sequence. Now you could, of course, obtain that pretty easily just by performing a summation directly. But the power of this is that it gives you a handle on, first of all, a polynomial. You get a polynomial that gives you these values, so you're getting more information. And also the technology allows you to jack this up. If we wanted the 100th summation, well, then instead of having to perform the summation 100 times, we could just jack up these exponents by 100, and then it'd be very easy to compute the higher summations. So obviously this difference transform that takes the original sequence and then gives us the top row of the difference table. That transform is an important operation in this story. So let's have a more careful look at it. So the difference transform called T of S. Let's look at it explicitly for a sequence S, say with terms A0, A1, A2, A3, A4. So the first difference is A1 minus A0, A2 minus A1, A3 minus A2, and A4 minus A3. That was a 5 sequence. This is then a 4 sequence. Now let's look at the difference of the difference. So the difference squared of S. So we have to take differences here. And it's instructive because now we're doing it algebraically and not with specific numbers. We see a little bit more clearly what's actually going on. So a2 minus a1 minus a1 minus a0. That gives us a combination a2 minus 2a1 plus a0. Similarly, the next one, a3 minus a2 minus a2 minus a1 is a3 minus 2a2 plus a1. And the final one, a4 minus 2a3 plus a2. And that's a 3 sequence. And the pattern will be clearer when we get to the third one. We take the difference of this one. So this term minus this term, what do we get? We get an a3, and here we're having minus 2a2, and then we're going to have to subtract another a2 over here for a total of minus 3a2. Over here we have an a1, and then we're going to subtract minus 2a1, which is like adding 2a1, so we're going to get 3 a1s. And altogether, then finally minus a0 as well. And that binomial kind of expression occurs also here. We get a4 minus 3a3 plus 3a2 minus a1. And then when we do the difference again, we get the binomial coefficients associated with 4. We get a sub 4 minus 4a3 plus 6a2 minus 4a1 plus a0. And please check that that's indeed the difference between those two numbers. So now we can write down what this difference transform is. T of s is going to be the zeroth elements of all of these consecutive differences. So starting with a0, then a1 minus a0, then a2 minus 2a1 plus a0, then a3 minus 3a2 plus 3a1 minus a0, and finally a4 minus 4a3 plus 6a2 minus 4a1 plus a0. So we end up getting another sequence, which is a 5 sequence, 1, 2, 3, 4, 5. It's the same length as s. So this transform T takes k sequences, which we might think of as columns, to these other k sequences, which are like rows of the difference table. Now we can summarize what we just did and put it into linear algebra terms, which makes it easier to compute, as follows. So if we start with the sequence S, A0, A1, A2, A3, A4, it's a 5 sequence, then the difference transform T of S is obtained by taking the original sequence as a column vector and multiplying by this matrix. Okay, it's a matrix which is very familiar to us. It's just like a Pascal or Harriot matrix, except it has some minus ones along every second diagonal below the main diagonal. So the top entry here will be A0. The next entry is minus A0 plus A1, which is the same as A1 minus A0. And then the next entry is A0 minus 2A1 plus A2, and then minus A0 plus 3A1 minus 3A2 plus A3, and finally A0 minus 4A1 plus 6A2 minus 4A3 plus A4. Now this is a very nice matrix. We're going to give it a name. Okay, we're going to call it, well, we're going to relate it to this thing here. This is the Harriot matrix, and let's put a 4 here to explicitly say this is like the truncation up to degree 4 of the Harriot matrix. H actually is an on matrix. It just keeps on going. So this one here is just a modification of this one by having these minus signs along these diagonals every second one. So let's call this the striped version of this one. Striped meaning we're adding minus signs to every second diagonal. And let's denote it by H sub 4 with a minus sign as a superscript. Now it is a very pleasant fact that these two matrices are inverses of each other. Okay? So H4 inverse, the inverse of this matrix, is exactly this striped matrix H4 minus. And so some pleasant combinatorics floating around here that we'll see the same pattern in other situations as we carry on. So now we have a good basis, a good grounding on some of the essential aspects of the discrete calculus. And actually, we have enough technology at our disposal to pursue quite a few interesting applications, and in the homework problems and exercises, you'll be able to have some fun with those. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.